Yes, I shared. I hope you see it.
I can see it. Very good. Okay, so it's a pleasure to announce the speaker of today is Mladen Savov, and he's going to talk about theory of Bernstein-Gamma functions and asymptotics of densities of exponential functionals of subordinators. Please go ahead.
Thanks for the invitation. And today I'll be speaking, as announced, on the theory of Bernstein-Gamma functions. And I believe these objects might be useful instrument in various studies, and I will try to exemplify this by our studies on asymptotics of densities of exponential functions of subordinators. But first of all, I would like to say that these functions are really a natural generalization of the gamma function, which we have seen playing a role in the workshop maybe 10 days ago. And the same way the gamma function is related, for example, to continuous positive self-similar Markov processes, the same way Bernstein-Gamma functions are related to non-continuous, right, continuous positive self-similar Markov processes, and they potentially can be useful tools in fractional calculus and also in studies of stochastic processes. And that's what I'm going to try to explain. So in these talks, I have basically singled out 4 aims. The first one is to introduce these objects, which are, honestly speaking, very simple as special functions compared to some other examples. Present their main properties, like Stirling type of asymptotic, especially. Then discuss their role in probability theory, and also discuss their role in a work of a colleague of mine in the field of fractional calculus and fractional equations, because I believe it is worth in the spirit of this workshop to present also this direction, although it is not a work of mine. But I'll be brief on this. And then I'll focus on a really more large-scale application of this function, and I will try to present you how they can be used to derive non-classical Tauberian asymptotic for exponential functionals of subordinators. And I will try to emphasize the properties that are needed, because I think they're universal, the same way the asymptotic and the properties of the gamma functions, and it potentially can be employed elsewhere. So before I introduce the object, I will briefly recall that a Bernstein function phi is such if and only if it has the form phi of z is potentially positive non-negative q plus linear drift, d is also non-negative, and then we have an integral term with respect to the measure mu, and mu is nothing else but integrable with respect to the minimum of y and 1, and this function phi is well defined on the complex half plane real part of z greater or equal than 0. These functions have been introduced more than 100 years ago by Sergei Bernstein, and they play a key role also, like, or if not a key role, it play an important role in analysis and complex analysis. For example, the first derivative of phi is the space of completely monotone functions, that is the Laplace transforms of Radon measures from 0 infinity, and all such type of properties. There is an excellent monograph on Bernstein functions published 10 years ago by René Schilling, Ren-Ming Song, and Zoran Vondracek, which I use as a reference. We also know that Bernstein functions are intimately related to stochastic processes. That's why they appear in this talk as well. And we shall see that the same way phi corresponds to subordinator, the same way Bernstein-Gamma functions will correspond to a specific probabilistic quantity, which will allow to study the latter. So now I can proceed with the introduction of the Bernstein-Gamma functions, and we shall start with the basic equation that is used for their definition. We take a very, let's say, well-known equation of the type fz plus 1 equals phi z fz, with condition f1 equals 1, and we impose this equation to be valid on the real part of z greater than 0, or the positive complex half plane, as I will refer to it. You see, the multiple is any Bernstein function other than the identically 0, because there is no point to introduce phi equals 0. And then if we have a solution of this equation on the second line, which is named W phi of Z, which is a Mladen transform of a random variable y, of positive random variable y. That is, it is the complex moment at the point Z minus 1. So this is this expectation. Then this solution is called a Bernstein-Gamma function. So I repeat, we have a solution in the space of Mladen transforms of positive random variables. So there must be a y which is strictly positive, such that its complex moments or Mladen transform solves this recurrent equation. It is a result, it's not a definition, it is a result that this equation has a solution, and this solution is a Mladen transform of a positive random variable, but it is a well-known fact, and we may use it for the introduction of these objects, which are the central of this talk, W phi or the Bernstein-Gamma functions. And when phi z is z, then our recurrent equation tells us that W phi of z is nothing else but the well-known gamma function that is widely used in our areas of study. I mean, the results that I present here, I mean, this existence of this solution is not our so say achievement. I'll mention something about our predecessors, but most of the results that are on W phi are present in the paper that you see in the footnotes, Bernstein-Gamma functions and exponential functions of Levy processes, which is co-authored with Pierre Petit and myself. Okay, so what functions may fall into the domain of Bernstein-Gamma functions? Of course, the classical gamma function is an example I have just presented. The double gamma function or Barron's function is also in this class. And also the Q gamma function is in there, as well as some other probably less known examples. I should emphasize that from the results we have, it's hardly possible to improve anything on these very well studied objects. I mean, they're extremely well studied. Some of them date back from the 18th century, some from the 19th. But it is interesting to see the universal, how our, more general or universal results for the whole class can be translated to these functions and open a way to study just the whole class as a whole rather than case by case. But nonetheless, I should stress that on these very old and well understood objects, of course, it is impossible to say something new. But the whole class is really what makes, I believe, is a positive difference. So the first result I'm going to present is about representations of W phi. We have a complete analogy with the gamma function. We have two types of representations. The first one is the well-known Weierstrass product representation. We have infinite product involving the basic quantity phi, the Bernstein function, which stays behind W phi. And if we plug in phi z equals z, of course, we get the gamma function. And we have even the counterpart, gamma phi of the Euler-Mascherani constant that appears in the Weierstrass product of the gamma function. The function that you see in red, 1 over phi of z, is the term that determines the analytical properties of W phi, the region where it is holomorphic, the region where it is meromorphic, when and how it can be extended additionally if phi of z really has some further analytical extension on the complex plane. So basically everything is dependent from the analytical perspective on this phi. We also have this logarithmic expression, which is also a direct counterpart of the gamma function. I'm not going to spell it out, but I should say that the difference with the gamma function is that this kappa measure that you see at the very end of the integral is rather inexplicit for this integral representation for the whole class of phi. And all results we have obtained, almost all results, are really dependent or were extracted from the infinite product representation. Only now with my student Martin Minchev, who co-authors some of these results, we are trying to utilize this integral representation to derive further or study further some probabilistic objects. But other than this, the majority of the results really stem from the first one, which is for me was rather strange because we have an infinite product, you just have a single integral, but this kappa measure is not as nice as it is in the case of gamma function. Now it's time to also say a few words about our predecessors. I mean, the infinite product, as you see it on the first line, has appeared in the work of Webster, 1997, who studied recurrent equations on the real line. So we had to just extend it to the complex line. So this was relatively straightforward. The function W phi, maybe not called, certainly not called Bernstein-Gamma function, is an object, has appeared in the works of Mark Hjor, the late Mark Hjor, Hirsch, Lilly, Ribeiro, and other researchers. And the integral representation is really thanks to Hirsch and Hjor in their work on this topic. So there is hardly any input from us in this direction other than the extension to the complex half plane, which is a technical but straightforward job. However, probably the first results regarding, or maybe considering W phi as a complex analytical function were derived by myself and Pierre. And the main direction we have worked on is the deriving Stirling type asymptotic for these functions. If we want to work with this object, we should be able to compute it or approximate it relatively easily. And what we have obtained with classical means that if we take on the real part of z greater than 0, of z greater than 0, then if z is increasing, modulus z is increasing, then W phi has this universal Stirling type asymptotic where you have e to the minus t phi. T phi is a constant which is in a semi-explicit form. It is an integral involving phi. It cannot be easily computed as a very simple expression, this integral, but it can be very well approximated, and certainly it's not numerically just triviality, I believe. And then the important part is not this constant, but the asymptotic. And the asymptotic is really half explicit in a way that the denominator is the square root of phi z plus 1. And the numerator is e to the power of the ret integral that you see, which is the logarithm of the Bernstein function behind W. And the integral is taken on any contour from 1 to z, as long as logarithm phi is analytical along this contour, and it always can be done for real part of z greater than 0. So, but generally speaking, the real carrier of the asymptotic is in the ret integral. The bottom really does not play a role in the overwhelming behavior of this function. So the main carrier is really hidden in the real part of this integral in the exponent. And this, using the complex logarithm, can be easily separated into two integrals. One of them is 1 to real part of z of logarithm phi dy, which is really dependent only on the real part of z, and it's basically completely explicit. One cannot expect much more to, I mean, something easier than this for any phi. But the second one is harder to deal with because it involves integration from 0 to the imaginary part of z, and also we have the argument, the angle of the Bernstein function that it makes with respect to the real axis, and you also have the role of the real part of z. So this term is more difficult to study when the imaginary part grows to infinity, and especially when both the imaginary and real part are diverging to infinity. But if you have bounded imaginary part or fixed, then the argument is a constant between minus pi over 2 and pi over 2, and then this integral becomes a trite. It's a triviality as long as if the imaginary part is bounded or fixed. Nonetheless, it presents the most problems in studying the Stirling type asymptotic. So let me consider the two cases. First, the real part is can be converging to infinity, and the imaginary part of z is fixed. So in this case, the second integral does not play a role because it is bounded, and all the asymptotic is really contained in the first integral from 1 to a. A is the real part of this explicit logarithm. And when the imaginary part is precisely 0, we have used it with Pierre in our paper on spectral expansions of non-self-adjoint generalized Laguerre semigroups, which appeared last year in the memoirs, as a crucial step to derive non-classical Tauberian asymptotic results regarding probability densities whose Mellin transforms can be expressed in terms of Bernstein-Gamma function. So we have used this asymptotic along the real line of this W phi for the purpose to apply some results of Bauer-Gamma and others. But this asymptotic really had to be complemented with a number of steps, but it was useful. What I believe is more useful, though, and may play a role, is when the real part is fixed, when A is fixed, and you start shifting B to infinity, the imaginary part. Then the logarithm of the absolute value of W can be written in a more difficult way by dividing and multiplying by B. But in this way, we introduce the blue quantity, which is the average angle the Bernstein function makes with the real line. This is really the average angle it has with the real line. This is the blue term. And then B is completely explicit, and that's just the imaginary part of Z. And now this quantity for fixed A is, I believe, more useful, because when we have Mellin or Fourier transforms of certain objects, let's say probability density functions, then these transforms involve W phi. Their inversion is taken along complex lines which usually have fixed A, fixed real part, unless you want to do more sophisticated analysis, as we shall be doing later. And then this asymptotic is, I believe, more fruitful, and that's why I spend more time. And that's why I introduce this average angle, which I'm going to describe on a graph. So what happens if you have C plus, the positive half plane, enclosed by the imaginary line in orange, then phi maps the half plane into the half plane. This is a well-known property. And the contour, the red contour, goes to some curve, orange curve that you see to the right. And then the black line is nothing else but the average angle the orange curve might have. I should stress out that it may be the case that an average angle does not exist, but in most cases, it actually does. And what it happens is that the asymptotic of the Bernstein-Gamma function along the imaginary line IY is really specified by this angle of the black curve, by this slope. And the most elegant example is when you take phi z equals z to the alpha, which you can see at the top of the slide. And then in this case, what you have is that actually the red curve is nothing else. The orange curve coincides with the black line, and it's a cone, because z to the alpha maps C plus to a cone, and z to the alpha is of course between 0 and 1, so that we can have such a Bernstein function. So this is a geometric representation. I'll repeat once more. If we have an average angle that is taken by this argument of phi, then what happens is that at logarithmic level W phi is really linear in terms of the imaginary part, in terms of absolute value of B, and then we have minus theta average in front. And if theta average is positive, which is quite often the case, then we can immediately say something through Mellin inversion. For example, the random variable y, whose Mellin transform is W phi, is really, one can use Mellin inversion because the function decays so rapidly that actually it is integrable with respect to the z minus a minus ib, especially when zeta is in R plus. And we can, what we can immediately deduct is that f of y is infinitely differentiable on the real line. And even more, thanks to the exponential decay of W phi, not only super polynomial, but exponential with speed, this theta average, then it's even analytical in some cone, which was also quite useful for our work with Pierre Petit. So one immediately gets something for this class of objects and their densities thanks to this Stirling asymptotic. And it has nice geometrical meaning. That's certainly the case. Now it becomes harder if we want to understand the asymptotic when both the real part of Z and the imaginary part of Z are going to infinity. In this case, we see that the first integral is what it is. It's relatively easy. But the second integral with the argument involves really convergence to infinity, both on its boundaries and inside the argument. And this makes it quite a bit harder to understand, and I shall speak about this and later when I start our discussion on exponential functionals and the application. But the moral of the story is that things become harder when z starts going to infinity, in not moving along complex line or horizontal to the real line, but when it just involves moving both imaginary and real part to infinity. And this really concludes the topic about these Bernstein-Gamma functions. What we saw that we really have good grasp of its analytical properties, the very first slides. We have relatively good understanding of the Stirling asymptotic, which has proved its usefulness in understanding properties of densities of random variables. And now I shall proceed with an example which is more on in the domain of fractional calculus and fractional equations, which is published in the work of Pierre Paty and Anna Srapionian, which appeared maybe a couple of years ago in fractional calculus and applied analysis. And what they did is the following. I'll be relatively brief on this subject. They took a Bernstein function which has no Q, basically has no killing term, it's only linear drift and integral. And through analytical manipulations, they represented the integral as in the following fashion. So we have dx plus x, and now integral from 0 to 1, vx by -1, this is change of variables, m of v dv. M of v is nothing else but the tail of the measure mu, taken from logarithm 1 over v to infinity. It's just a well-defined decreasing function. It's not a problem. And then for alpha greater than 0, they introduced a fractional derivative in time acting on a function f in the following way. So this derivative depends on phi. You have diamond phi, and phi is related to m. This is the link that phi gives you m, and you use m to define this fractional derivative. And then you have a classical term, t to the 1 minus alpha f prime t. And then you have t to the minus alpha and an integral, which is written almost like a multiplicative convolution, a product convolution, but it still involves f prime and this kernel m, which stems from the Bernstein function. And then this fractional derivative is, okay, let's say well defined. And they wish to use this derivative to introduce fractional equation, which describes a class of of stochastic processes in a good way. So they want to introduce really a large class of stochastic processes whose equations are really in terms of this fractional derivative in time. So what they did is they took an increasing alpha self-similar process chi, which is independent of a good Markov process. And what they want to do is to time change x in a good way so that they get a non-Markovian process, the same way we observed in the workshop last week. But to do so, I shall first have to say a few words about chi, this increasing alpha self-similar Markov process. It is well known that any positive self-similar Markov process, even more increasing one, chi can be represented as the initial position x times the exponent of a Levy process, psi, in this case a subordinator, increasing Levy process, suitably time changed, and this is known as the Lamperti transformation. In this sense, to any chi, there corresponds a subordinator psi with Laplace exponent phi. So this is the link. The phi that I introduced for the fractional derivative is linked to psi, which is the Lamperti transform, whose Lamperti transform gives chi, which is an increasing self-similar Markov process. Increasing self-similar Markov process is probably not, certainly not as well studied as subordinators, or not that much used as subordinators, but intersection between the alpha self-similar Markov process, the increasing ones, and subordinators happens on the stable, alpha stable subordinators. But other than this, they're not directly related. So you see that to any subordinator, there is alpha self-similar Markov process and vice versa, but it happens through a rather complicated one-parity transformation. So this is not a triviality for sure. Okay, we have this object, it is linked to a certain function phi. This is the moral of the story for this talk, that to any alpha self-similar Markov process, there is phi that links it. And what they did, they took this increasing chi, and introduced the process zeta, which is the right inverse, and constructed y of t, which is x times with zeta. This time change, y of t equals x time change with zeta, is precisely what we observed in the workshop in the talk of Bruno, myself, and other researchers when a process is describing motion in porous media or media with traps were introduced and studied. But in this case, zeta is independent of x, so we have no dependence, but it is not stemming from a subordinator, but it comes from alpha self-similar Markov process. And with this time-changed process, what one can do, one can show is that one can relate a Cauchy-type problem, which involves this fractional derivative that I have introduced, with acting on u, which equals the generator of x acting on u with the initial condition u0 x f of x, basically this Cauchy-type problem. And this equation is linked to y by the virtue of the fact that the solutions of this Cauchy problem are really the expectations of the process y. So if you take f of y, starting from x, and the expected value is really this function utx. So basically, there is this link. I really wanted to make this link in this talk because you don't see Bernstein-Gamma functions in these 3 slides, but behind the scenes, the role of the Bernstein-Gamma functions was substantial. And what I want to send across as a message, that they can be useful tools for the proof. You see, they don't appear here explicitly, but they certainly do appear in the proofs in this paper. So it does rely on them for obtaining of these results. And the next step will be really to make a transition to the area where the Bernstein-Gamma functions have been mostly used so far. And this is for the study of exponential functionals of Levy processes. This has been our main motivation to introduce this quantity. We observed that it can be used elsewhere, but we did it because we observed that we could study exponential functionals of Levy processes in a unified way. Before introducing the exponential functional, I will recall that a Levy process psi is a potentially acute stochastic process with stationary and independent increments. I would like to highlight that we allow in this definition not only processes with stationary and independent increments, but also with potential killing at exponential random time. This makes the things more universal, and one can do everything at one go. Then these random processes are well known, the Levy processes, to be determined by the logarithm of their expectation of e to the z psi 1 that you see as equation, which is nothing else but by the Levy-Hintgen exponent psi, which has q, which is non-negative. This is the potential killing. We have a linear drift az. We have Brownian term sigma squared over 2z squared. And we have the well-known integral with respect to the Levy measure pi, where the quantities are non-negative for the killing term. A is arbitrary linear drift, sigma squared is of course non-negative, and the Levy measure has to be integrable with respect to the minimum of x squared and 1. Pi describes the jumps and the intensities of the respective, and their intensities of the respective process psi. So what I would like to mention, that if q is 0, then the process is conservative and it's not killed. So this is a slight extension of the definition. But it is an unuseful one. And it is this object, analytical object psi, has a well-known Wiener-Hopf factorization. So I should highlight that psi of z itself is well-defined usually only on the imaginary line IR. but it factorizes as a product of two Bernstein functions, phi minus and phi plus, as you can very well see on the screen. And phi minus and phi plus are, of course, very well defined on half planes because they are Bernstein functions. One is taken at the argument z, the other at minus z. And these functions, phi plus minus, are not simple analytical objects that are byproduct of some analytical results, but these are actually related to the maximum and minimal processes or the ladder heights of Xi. We shall use mostly this analytical representation, but one should know that behind this phi plus and phi minus, there is a very deep and beautiful probabilistic interpretation. But nonetheless, this linear Hopf factorization will be key for studying the main object. And the main object is really the exponential functional in this talk, in this part of the talk. What we have, if Xi is a Levy process with Levy-Hintsching exponent psi, then we can define the exponential functional I psi, so psi is related to Xi, as the integral from 0 to EQ. EQ is the exponential killing, potential exponential killing of Xi, e to the minus Xi s ds. EQ, as the clock of killing, is independent of the process. It has exponential distribution with parameter q, and it is infinity if q is 0 and the process is conservative. The exponential functional has appeared in many studies and is used also as a useful instrument, and that's why I want to present how the Bernstein-Gamma functions are useful for their study. I should mention that I psi is finite if and only if q is positive. We have killing, finite horizon, or psi of s goes to plus infinity, so that this integral is finite if we integrate it on infinite horizon. What has gradually become clear is that if one gives you exponential functional I psi, one can compute its Mladen transform or its complex moments, if you would like, in this expectation, as the product of three terms: the Bernstein function phi minus at 0, gamma z divided by the w phi plus z, and w phi minus 1 minus z. And this always holds as a minimum between the real part of z in 0, 1. And I recall that psi of z has this linear Hopf factorization. We take phi plus and phi minus from there, and necessarily phi minus is positive at 0 when I psi is finite. So there is no restriction. One can study and obtain the Mladen transform of absolutely any exponential functional in terms of these three products. And I should say that the result is not obtained at one go. There has been a sequence of studies to really come to this final, most general solution, and there are contributions of Mark Kjor, Dufresne, for Petit, Carmona, very important contribution of Maulik and Schwartz, Alexei Kuznetsov, Lili, Ribeiro, and many, many others if I forget somebody. So, but eventually in our paper with Pierre, we were able to understand that the Mladen transform can be universally explained, represented in terms of Bernstein-Gamma functions. And it gives results, and I'm going to quickly present them before I get to the final point. So Fi psi first is infinitely differentiable unless Xi is a compound Poisson process with positive drift. This is interesting result because the conjecture was that the density of the exponential functional is infinitely differentiable if you have infinite activity of the Levy measure. So it's not a compound Poisson process, but it turns out that it's also infinitely differentiable if it is a compound Poisson process with 0 or negative drift. And also, if it has positive drift, we have an explicit quantity which tells us how many derivatives you can still have on the density before they may break down. So almost complete picture of the differentiability properties of densities of exponential functionals. Then the blue term that you see in the expression is responsible for the behavior of the density at infinity. I shall spend a little bit more time on this. The red term determines the behavior at 0 of the density, and the green term is probably the most curious one because it depends implicitly on the killing term q, and when q goes to 0, the green terms, allows for the study of the measures of exponential functions on deterministic horizon from 0 to t when t goes to infinity. And this quantity on deterministic horizon is far more difficult than the exponential functions we are now considering. And this is an ongoing work with my student Martin Minchev. And this usefulness is probably the most unexpected, at least for me, because the other two one can explain. But here, this hidden dependence on Q and that it allows for the study of such measures that you see of deterministic, related to deterministic horizon exponential functions is somewhat surprising. All these results are contained in this paper that you can see at the footnote. But I want to say a few words about the large asymptotic behavior, because under very general conditions, what one can prove is that not only the density, but even their derivatives are asymptotically a constant n, which is explicit, at x to the u minus minus n, where u minus is precisely the first negative root of f minus. And this asymptotic result contains basically all the results about suprema of stable Levy processes. They have been studied in a sequence of papers of annals of probabilities. And this result basically contains the majority of these results in its hands, because it looks at stable processes from the perspective of self-similarity, not from the perspective of Levy process. And this is a rather general result. But even more, in all cases, if you take the tail of the exponential functional at logarithmic level, it converges to explicit quantity a minus if you divide it by logarithm of x, and a minus is not finite if and only if xi is subordinator, which tells us that unless xi is subordinator, the tail of the Levy measure is roughly polynomial. And that's okay, it's satisfactory because it basically complete generality unless you have a subordinator. The difficulty starts when a minus is minus infinity and you have to consider exponential functions of subordinators. I recall that a subordinator is a non-decreasing Levy process which has non-negative linear drift and sum of jumps. In this case, psi of z is simply one Bernstein function minus phi minus of z, and the Mladen transform of the exponential function of subordinators is really a gamma function divided by the respective Bernstein-Gamma function w phi. At first sight, it is an easier object than the one for the general exponential functionals, but for the asymptotic studies, it's harder to understand because this Mladen transform does not have a pole on the real part of z greater than 0, and one can really, it's a homomorphic there. And we wish to study now exponential functional, which is taken with respect to the subordinator. So we have integral from 0 to the exponent eq e to the minus xi s ds, where xi is subordinator. And what we have managed to prove with Martin is if xi is a Griffith subordinator, otherwise it's pointless to study, it's a bounded quantity, with the Bernstein function phi, which has the following condition that the limit supremum of x phi prime x divided by phi of x is less than 1, then for any n greater or equal than 0, the derivative, the density and its derivatives and derivatives have completely explicit asymptotic expression. And it's a somewhat non-classical asymptotic, non-Tauberian, non-classical Tauberian asymptotic, which is visible in this exponent, which contains two quantities, phi star and y far star, which are basically explicit because phi star is x over the given Bernstein function, and var phi star is simply the inverse of phi star. So this asymptotic is explicit, and the constant is also explicit in terms of an integral, which can be computed. And that's a really explicit result for a very large class. And one has to offer some discussion on this condition. This condition about this limit supremum is really, I think, very mild one, and it's equivalent to the condition of positive increase of a Levy measure. And very interestingly is that 3 months after we submitted this work for refereeing, Benedicte Haas has actually supplied similar results when n equals 0, i.e. only for the density, but in her work, the constant is implicit. And she has precisely the same condition, which is tells us that probably this is necessary. And she does this work, her work, with a very smart method which involves integral equations. I believe that Melanin inversion, which I'm going to present if I have enough time in detail, is, I think, the natural way, because it's a very universal approach, but her smart approach was in using integral equation. And she went a bit better on the speed of convergence. So in our asymptotic, we had a speed of convergence 1 over square root of var phi star, where she has speed 1 over var phi star x. But on the other hand, her approach does not allow her to work out the constant, and perhaps may have some difficulties for derivative of the density. But I have to emphasize that it's really a smart way to approach this problem, because the classical, I think, would be with Melanin inversion. And that's what I'm going to say a few words about. So if we have exponential function of subordinator, our Melanin transform mi psi of this density is very good. We can take Melanin inversion for any real A. So we invert along A plus IB, like in the argument of the Melanin transform. We take the Melanin inversion and we obtain the density, which is infinitely differentiable. Okay, that's good. But how can we extract the asymptotic? It's certainly the case that for any fixed positive A, mi psi as a function of B is A1R, and then the limit of xa fi psi is 0. So certainly we don't have polynomial decay as something that could be expected, because we have no pole for this Melanin transform. So we have to do something like the saddle point method. We cannot just fix on A and for any x use this Melanin inversion in a fruitful way. We would have to balance it, or how to say, to choose A according to x, so that we extract the right asymptotic. And to do so, what we do, I introduce these quantities, phi star, which is x over phi. One doesn't have to remember it, just explicit quantity, and var phi star is inverse. And we have at the top, we have the Melanin inversion. And what we do, we just take mi psi and plug in its Stirling asymptotic. And when you plug in this Stirling asymptotic, you see the red term at the exponent, you see this phi star at the bottom, and you see these exponential terms in the integral. We have three functions you have to analyze and understand, but they're just taking the Stirling asymptotic and plugging it into this Melanin inversion. G of A is completely explicit. It's 1 to A, the logarithm of phi star, and that's completely explicit. One cannot do anything better. And the first step would be to get rid of this x to the minus IB and this U function. And then what we shall do is we are going to apply the saddle point method to this quantity up front. So the term involving x to the minus IB really causes no troubles. I'm not going to spend time on it, so this just vanishes. Then for fixed A, we minimize this function, as it is very classical to do, and we obtain that for given x, ax must be var phi star x, so it is completely explicit. And when you plug in ax with the respective var phi star x, you obtain this explicit expression, and the asymptotic of fi psi at infinity is really a constant, explicit constant, with this exponent, which is also explicit, and it's really the main asymptotic term. However, you are left with an integral which is not explicit and whose asymptotic you have to understand if you want to derive really the most precise asymptotic in X for this density. And to do so, one has to employ and understand Bernstein-Gamma functions. How it is done? It is done by studying this function A, which is the only inexplicit term in this integral. First, you split this infinite horizon in appropriate manner. You truncate to a good function g of x, and you may show that this integral really behaves asymptotic like square root of 2 pi var phi star prime of x. So this is a classical Laplace method. It is conducted in the following way. You take your function A, you take it from the Stirling asymptotic. This is the argument I spoke about, but rather than phi, you have var phi. You have phi star, nothing different, nothing changes. You represent this argument as the imaginary part of the logarithm, and for any b smaller than g of x, you can represent via Taylor expansion a var phi star x plus ib as square part of b and cubic part of b. It turns out that on this domain, the cubic part does not play a role, and everything is contained in b squared. And once you plug in this Taylor expansion, a classical Laplace method gives the result that I am claiming beneath. I have to say that initially this was hard to understand what to do, because the Laplace method is easily used when the parameter in the Laplace method, in this case x or var phi star of x, is a multiple of the integrand, which is b. Here the function depends on both of them, and one has to be careful to do the things properly. That makes the things harder. It's not like multiplying b by var phi star x and then it's clear what to do. Here one has to be subtle, but obtains this asymptotic. So that's fine. But what to do with the remainder term when b is greater than g of x? What to do with this integral when the absolute value of b is big? We have to show that it has O small of 1, the asymptotic of the previous one, which is precisely square root of 2 pi multiplied by the derivative. And to do this, we have to understand very finely the properties of a, of this function a. First, we do a reduction, which changes instead of considering the integral from gx to infinity, by a change of variables, one can reduce to the case when the integral is fixed from 1 to infinity at the cost of var phi star coming out. And the function a is also modified slightly by this change, and it is highlighted in blue for your convenience. And this is the function one has to understand and show that this integral to the right is really of smaller asymptotic order than the previous one. And to do this was a hard work, because one had to understand the blue function a, which is of the type a small times 1 plus ib. This is precisely the form of this function. And this is through simple computations, is simply a integral from 0 to b, the argument of phi star a plus 1 plus I w dw. And now one has to understand the argument of phi star. There is no way to understand this function without appealing to the angle of Bernstein functions, or in this case, x divided by Bernstein function phi star is making with the real axis. You cannot do away with this. And one theorem we have managed to prove, and I believe is important, is that under the this condition for the Bernstein function, if I take a positive t0 and take any t greater than t0, and that there is a constant a t0, such that if a is bigger than this constant, there is a constant also depending on t0, such that the argument of the Bernstein function taken at the point a, basically on a ray. The ray is a1 plus it, and this does not become too close to pi over 2. It may converge to pi over 2, but it's not better than a linear order 1 over t. That's very important. And when you have this for the Bernstein function, then phi star is simply x over the Bernstein function, and the pi over 2 as the argument is naturally to disappear, and the inequality goes the other way. It's the argument of phi star along the ray a1 plus it is really greater than ct0 over t. Even more, if you have additional condition, then you can show that the argument is actually strictly positive. I shall not dwell on this result, but this is very important because it translates to Bernstein functions, Bernstein-Gamma functions, excuse me. And when one does some analytical, let's say Marin inversion, Fourier inversion, you have exponential decay, and you really can get quite strong properties for the respective densities or objects you are studying through Marin inversion. And using the green result, here in the middle, you can show that your vital quantity A taken at the var phi star 1 plus IV is really greater than a constant var phi star x logarithm V. And this is completely explicit. And this allows you to study this rather complicated integral that we started off with. And once you substitute the bound for minus A, then you get an explicit term that you have to proceed and understand. It is not too difficult. And from there, one can really deduct that the remainder term that you see at the very bottom here is really of smaller order than the asymptotic of the previous integral. And then one can come back to the theorem and simply conclude the main result, that the derivative, the density and any of its derivatives have explicit asymptotics in terms of var phi star and speed of convergence on 1 over square root of var phi star. And I emphasize that Benedicte has, for n equals 0, has speed 1 over y var star of x. And on the way, we had to improve the Stirling asymptotic of the Bernstein-Gamma function. I have not spelled it out, but it is really related to these estimates of the argument of the Bernstein functions, which are general. They're simply for this class, which is a well-known class of functions. And I do not want to burden this presentation any further because there were a number of technical details, and I would like to thank you for attention.
Yeah, thank you very much for this very nice talk. So it's really impressive how many explicit formulae you can derive and also apply these formulae to probabilistic problems. Okay, so are there any questions, comments? So just speak if you have a question. Okay, it doesn't seem to be the case. Then thank you very much for the very nice talk again.
Very much for the invitation and have a good day.
Okay, and I remind that there is another talk at 2 today, and so hope to see all of you again at that time. Bye-bye.
Bye-bye.